and 1,000,000 years after time zero, the solar system's method for sorting out its planet-building material is clear. They're separated by the different temperatures in the disk. Close to the protosun, temperatures above 2,000 degrees vaporize everything. But about 5 million miles out lies the rock line, where it's cool enough for metals and minerals to turn solid. Much farther out lies the snow line, where it's as much as 375 degrees below zero. Cold enough for water, methane, and ammonia to freeze into ices. The particles sticking together are microscopic at this point, far smaller than the melting sugar crystals. And as cotton candy illustrates how these solids accrete in the solar system, another amusement park attraction shows what makes them grow. Bumper cars wouldn't be much fun without collisions. And in the solar system, without collisions, there would be no growth, no accretion.
The accretion collisions that were happening in the early solar system are of the kind that allow objects to stick together through various kinds of essentially friction-type processes where you have things getting stuck together just due to mechanical interaction.
In the inner solar system, the process is time-consuming, as tiny cosmic dust balls form slowly, stuck together only by random collisions in their orbits around the early sun. But in the outer solar system, the story is dramatically different. The giant planets are about to burst into existence in a cosmic blink of an eye. Beginning as a cloud of gas and dust, the making of our solar system will take 700 million years. Now, just 2 million years after its birth, the young system takes its first steps in creating a family of planets that one day will be as diverse as Jupiter, Saturn, or the Earth. For now, though, they are chunks of matter continuing their roller coaster ride in the turbulence of the solar nebula. The thick, rotating disk, made mostly of hydrogen gas, is embedded with solids. The inner zone is filled with small chunks of rock, but outside the boundary known as the snow line, there are also ices of methane, ammonia, and water, which dominate the outer disk, and for good reason.
They're all hydrogen compounds of one form or another, and hydrogen is the most abundant element in that region of the solar system at that point. That abundant hydrogen is combining with elements such as oxygen to form the water, or carbon to form the methane, or nitrogen to form the ammonia, and giving us those compounds which are then freezing out.
Continual collisions amid the turbulence make tiny specks of dust and ice stick together through friction and static electricity until they're large enough for gravity to take over. Eventually, they become planetesimals.
Planetesimals were the original building blocks of our solar system. They're incredibly small, only about half a mile to a mile across, but there were countless numbers in the early solar system. It was simply littered with them.
These half-mile planetesimals will eventually form full-scale planets, but of distinctly different sizes. That's what Ryan Chan of San Mateo, California, wanted to ask the universe by writing, why are the planets closer to the sun smaller than the giant planets farther away from the sun?
Ryan, the inner planets are smaller than the outer planets because the inner planets didn't have much material from which to be made, just metals and rocks and things like that. The outer planets, after forming an Earth-like core, were able to attract ices of water, ammonia, methane, and carbon dioxide. That made them get bigger. And then they gravitationally attracted gases, becoming much, much bigger.